Hello there, and welcome to the Sleepy Space Channel. Nothing on the moon is especially likely to kill a settlement, and that is not the reassurance it sounds like. A place like that does not end anyone. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. The ground underfoot is nearly half oxygen by weight, and holds almost no nitrogen and almost no carbon, which happen to be the two elements a human body and everything it eats are built from. The polar ice is a fixed balance rather than a cycle. The sites with both sunlight and water number in the low tens across an entire world. And the size a settlement is allowed to reach is set by how much heat it can throw away. Tonight, we work through the whole ledger, one column at a time, and find out what living there would actually cost. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Settle in. Let the room go quiet around you. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The difference between surviving and staying. Almost everything ever written about living on the moon is written about the first few months. That interval is the comfortable one, in the sense that its problems all have known answers. A pressure vessel holds air. A suit holds pressure. A layer of rock stops most of the radiation. A reactor or a field of panels supplies power, and a rocket arrives on a schedule with everything the place cannot make. An outpost is a machine with a delivery calendar attached, and calendars can be met. A settlement is a different kind of object, and the difference is not size. It is defined not by whether people are alive inside it, but by whether the place can absorb time. Machines age. Seals harden. People accumulate radiation and lose bone. Inventories drain and are refilled by decisions made 250,000 miles away. The question that separates an outpost from a settlement is whether a place gains capability faster than it gains obligation, and on the moon it does not. The reason is unsettling in its simplicity. It is chemical long before it is political. There is a quiet arithmetic underneath all of this, and it is worth setting out at the start, because every part of this episode is an entry in it. On one side of the ledger sits everything a permanent human presence consumes without pause. Breathable atmosphere. The buffer gas that fills most of that atmosphere. Water for drinking, for crops, for coolant, for shielding. Calories. Electrical power. The capacity to throw away heat. Spare parts by the tens of thousands. Medicines with expiry dates. And human beings, each of them working inside a lifetime radiation limit that is being spent every hour they stand there. On the other side of the ledger sits everything the moon can supply from its own material, without an import. That column is not empty. It is, in places, generous. But it is generous in a very particular pattern, and the pattern is what this whole night is about. The moon gives just enough of almost everything to make staying look possible, and never enough of anything to make leaving unnecessary. That sentence is the shape of the trap. It is not a dramatic trap. Nothing about it is sudden. The moon does not attack a settlement, does not throw weather at it, does not close in around it. It simply fails to supply, patiently, for as long as anyone is willing to stay. And the failure has a direction. A settlement that succeeds becomes larger. A larger settlement has more people, more modules, more machinery, more surface area, more heat to shed, and more parts to replace, and every one of those additions is denominated in the things the moon cannot make. Dependence on Earth does not shrink as a lunar settlement matures. It grows. It helps to hold two words apart from the beginning. A starter is a resource that lets a process begin. A supply is a resource that lets a process continue without end. Lunar oxygen is a genuine supply. It is locked into the rock in enormous quantity, and the rock is not going to run out. Lunar water is a starter that behaves like a mine. It exists. It is real. It does not renew, and every liter taken from it is a liter that will not be there for anyone else. Lunar nitrogen and lunar carbon are not starters at all. They are trace contaminants that happen to be the elements living bodies are largely assembled from. Everything else in this audit follows from that pattern, repeating down the whole list. Consider what has actually happened on the moon so far. People have stood on that surface for hours, and in the longest cases for a few days. Nobody has ever spent a continuous month there. There is no record anywhere of a human body living for a long stretch at 1/6 of its normal weight, because no such stretch has ever occurred in any species at any age. The entire question of permanence rests on a stack of interpolations, and we will come back to that when we reach the people themselves. Meanwhile, the raw material for building is never the constraint. Loose broken rock covers the whole moon, 4 or 5 meters deep across the dark ancient plains, and 10 or 15 meters deep or more across the older, paler highlands. There is no shortage of mass to pile over a habitat, no shortage of ground to cast into blocks, no shortage of anything measured by the ton. The moon is not poor in matter. It is poor in specific elements, and in the particular arrangements of matter that a working machine requires. There is a deeper reason for that poverty, and it is worth understanding early. On Earth, useful elements are concentrated for us before we ever arrive. Water moves through rock and dissolves metals out of it. Heat and pressure drive them into veins. Plates slide under one another and cook whole regions until the valuable material separates from the worthless. Every ore body on our planet is the end product of machinery that ran for hundreds of millions of years. The moon has none of that machinery. It has no plate movement, no running water, no atmosphere to sort particles by weight. Its useful elements were never gathered into deposits, so they sit thinly dispersed almost everywhere, in roughly the concentration they arrived with. The often mentioned lunar fuel, a light isotope of helium implanted by the solar wind, sits at a few parts in a billion. Collecting a single ton of it would mean processing something in the region of 100 million tons of soil. The surface itself is larger than most people picture. Laid flat, it would cover roughly the area of Africa and Australia together. And yet the number of places on it that satisfy the two conditions a serious settlement needs, near continuous sunlight and access to buried ice within a practical distance, is somewhere in the low tens. That narrowing, from a world the size of 2 continents down to a handful of ridges, is one of the stranger facts in this whole subject, and it waits for us a few parts from now. There is also the matter of what failure looks like. An outpost fails by aborting. Something breaks, the crew leaves, and the machine is switched off with a schedule and a plan. A settlement fails differently and much more quietly. It fails by insolvency. There comes a year in which the import bill is larger than anyone is willing to pay, and the population begins to decline, not because the place became lethal, but because it never became worth it. That is a strange kind of ending for a world. Nothing dramatic happens at all. The launches simply become less frequent, and then they stop. None of this is an argument against going. It is an argument about what the going actually is, and about the gap between two words that sound almost identical. Surviving on the moon has been demonstrated. Staying on the moon has never been attempted, and the reason has very little to do with courage or engineering skill. So this is the shape of the night ahead. We will take the ledger apart, entry by entry, slowly, the way an auditor would, rather than the way an explorer would. Air first, because it is the entry where the pattern shows most clearly. Then water, then the ridges everyone wants, then the dust, then the machinery, then the bodies, then the children, then the food, then the heat, then the distance that only looks small. At the end, we will add the columns together and see what independence would actually cost. The moon will be exactly where it has always been throughout. It has not changed in any way that matters for 4.5 billion years, and it has no opinion about any of this. That is part of what makes it such a demanding place to think about. There is nothing to argue with. There is only a list of things that are present and a list of things that are absent, and the second list turns out to be the one that decides everything. We begin with the first thing anyone needs, and the first place the pattern appears. Part 2. The air that has to be imported. Oxygen is the easiest thing on the moon to obtain, and it is the smallest part of the problem. Between 40 and 45% of lunar soil, measured by mass, is oxygen. It is not lying about loose. It is bound into silicates and oxides, held in some of the most stable chemical bonds in nature, and prizing it out takes energy and heat and patience. But it is everywhere. Every shovelful of ground on that world is very nearly half oxygen by weight, and no settlement anywhere on the surface would ever be more than a few meters from a supply that could not be exhausted on any human timescale. Two routes to it are reasonably well understood, and they trade against each other in an instructive way. The gentler route uses a mineral common in the dark plains, an iron and titanium oxide, and reduces it with hydrogen at moderate temperature. The chemistry is mild, and the hardware is manageable. The yield is poor. Only the oxygen loosely attached to iron comes away, which works out at something like 1 or 2% of the feedstock mass. To produce a single ton of oxygen, a plant would move, heat, and process on the order of 100 tons of soil. The more productive route melts the regolith outright and passes a current through it, liberating oxygen directly from the melt and leaving a crude metal alloy behind as a byproduct. The yields are far better. The temperature is around 1600 degrees, and the unsolved problem sits at the anode, because almost no material yet found survives immersion in molten rock and pure oxygen at once for any length of time. Whichever route a settlement chooses, it will be running a hot, hungry, continuous industrial process simply to breathe. The metal that comes out of the melt is worth a note of its own. It is an alloy of iron, silicon, and aluminium in whatever proportions the local ground happened to hold, which makes it useful for crude structure and useless for anything that requires a specified property. It will hold a wall up. It will not become a bearing. And none of that is the real difficulty, because a breathable atmosphere is not oxygen. Pure oxygen at low pressure is survivable. Early spacecraft used it, and people lived in it for days at a time. But it is a fire environment of a kind that no habitat meant to last decades will accept, and it carries slow physiological costs over months. What people actually live inside is mostly something else entirely. Roughly 78% of the air on Earth is nitrogen, and the entire function of that nitrogen is to be present. It does no chemical work in the body. It fills volume, holds the total pressure at a value the body finds unremarkable, and dilutes the oxygen enough that a spark does not become a catastrophe. It is the part of every breath that does nothing, and it cannot be removed. The moon does not have it. What nitrogen exists in lunar soil was not made there. It arrived one particle at a time, driven into the outer few tens of nanometers of individual grains by the solar wind over billions of years, and it sits at concentrations of a few tens of parts per million. Perhaps 100 in the oldest and finest soils. To fill one modest habitat with buffer gas would mean heating and outgassing a quantity of ground measured in tens of thousands of tons, and then doing it again for the next module, and again for the leak rate. There is an unkind detail buried in how that nitrogen is held. Because it was implanted from outside, it lives only in the outermost skin of each grain, which means the richest soils are the ones with the most surface area for their mass. Those are the finest soils, ground down and reworked by billions of years of small impacts. And the fine fraction, as we will see later tonight, is the single most destructive material on the moon to work with. The soil that holds the most nitrogen is the soil that does the most damage to the machine trying to extract it. The frozen deposits at the poles hold a little nitrogen too, and a little carbon, delivered by comets and by the debris of the outer solar system, and held in permanent shadow ever since. It is a real source. It is also a small fraction of an already small deposit, and drawing on it means spending the same finite reserve that supplies the settlement's water. Every route to nitrogen on the moon either moves mountains of soil or borrows from the ice. Seas will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Every polymer, every plastic, every fiber, every seal compound, and every calorie a person eats is built on a carbon skeleton, and the moon holds carbon at roughly the level of a trace impurity. So here is the pattern in its purest form, arriving in the very first thing a settlement needs. The moon can supply the fraction of the air that keeps a person alive, and it cannot supply the fraction that fills their lungs. The bill does not stop at the first fill either, and this is where a settlement differs most sharply from a mission. Air is not a one-time purchase. Habitats leak, continuously and by design, tolerance rather than by fault. Gas escapes through seals, through hatch interfaces, through every penetration where a cable or a pipe crosses the pressure wall, and through the slow permeation of the wall itself. Every airlock cycle vents some fraction of a chamber's atmosphere to vacuum unless it is pumped down first, and pump-down recovery is standard practice and never complete. The residual is simply lost. The loss is proportional to the number of times people go outside, and the number of times people go outside rises with the size of the settlement. Inside, the chemistry runs constantly. One adult consumes something like 800 grams of oxygen a day and breathes out roughly a kilogram of carbon dioxide. That carbon dioxide must be captured and then, in any closed system worth the name, broken back down so the oxygen can be returned to the air. What is left over is carbon, in solid form or as methane, and in a place with no carbon source, every gram of it that gets vented overboard is a gram that will eventually have to arrive on a rocket. Then there are the contaminants nobody thinks about until they accumulate. Polymers off-gas slowly in a warm, sealed volume. Equipment faults release combustion products. Ammonia builds up from waste processing. All of it has to be caught in catalytic beds that are themselves consumables with finite lives, and all of those beds are imported. The buffer gas requirement scales with pressurized volume, which is the detail that makes it a permanence problem rather than a startup problem. A settlement that grows its living space tenfold grows its nitrogen import tenfold, no matter how good its recycling becomes, because the new volume has to be filled with something before anyone can stand in it. And the crops, when we reach them, will want nitrogen too, in a fixed and plant-available form, which is a second and entirely separate demand on a supply that does not exist locally. There are ways to soften the number. Lower the total pressure and raise the oxygen fraction, and the nitrogen bill shrinks. The cost is fire risk, tighter materials selection, and longer pre-breathe protocols before every excursion outside. The bill never reaches zero. It only becomes smaller and permanent. That is the first entry in the ledger, and the shape of it will be familiar by the end of the night. The moon hands over the difficult half of the atmosphere for the price of heat and electricity in unlimited quantity forever. And then it stands there, entirely still, unable to supply the easy half, the inert half, the part that is just there to take up room. A city on the moon could quarry its own oxygen out of the ground beneath its feet and would still, every single day, be breathing imported air. Part 3. Water that behaves like a mine. The discovery that changed the entire argument for lunar settlement was ice. It is real, and it is considerably less useful than the headline suggests. The moon's spin axis is tilted only a little over 1.5 degrees, which is almost perfectly upright. On Earth, a tilt of 23 degrees is what gives us seasons, long summer days and long winter nights. With almost no tilt at all, the moon has no seasons worth the name, and near its poles the sun does something it never does anywhere else in the inner solar system. It circles the horizon. It does not climb. And into the deepest crater floors near those poles, it has not shone at all for something in the region of 2 billion years. Those floors are the coldest places anywhere near us. Temperatures there sit below -230 degrees, and in the very deepest traps they fall to a few tens of degrees above absolute zero, which is colder than the surface of Pluto. Cold like that does something specific. It holds volatile molecules in place. A water molecule that wanders into such a trap and touches the ground will, on average, stay there longer than the solar system has existed. So over billions of years, water delivered by comets and by carbon-rich debris, and water made in tiny quantities by the solar wind reacting with oxygen in the rock, has drifted across the surface, found the cold, and stopped. We know it is there from 3 independent directions, which is why the finding has held up. Orbiting instruments that count neutrons see a clear hydrogen enrichment over both poles, because hydrogen slows neutrons in a way nothing else does. Instruments that read reflected light see the spectral signature of hydroxyl across even the sunlit ground, produced continuously as solar wind hydrogen reacts with oxygen locked in the minerals. And a spacecraft was deliberately flown into a shadowed crater floor so that the plume it raised could be examined from above, and water was found in it directly. That is the deposit. And the moment anyone tries to use it, 3 separate problems begin. The first is that it is not a sheet and not a lake and not a buried glacier. The evidence points to ice, bound within the soil itself, mixed through the top few meters of ground at concentrations of a few percent by weight, distributed unevenly and patchily. Mining it means excavating frozen, abrasive soil at cryogenic temperature, in permanent darkness, on the floor of a crater, using power that has to be generated somewhere sunlit and carried in by cable or by a reactor set down beside the work. Ice at those temperatures is mechanically harder than granite, and it gets harder as it gets colder. The machinery has to work where most lubricants are solid, and most steels have gone brittle. The second problem is thermodynamic, and it is the quiet one. To release a few percent of water by weight, the entire mass of the host soil has to be warmed. There is no way to heat only the ice. Every liter extracted, therefore, carries the energy cost of raising many kilograms of rock through hundreds of degrees in a place that has no ambient heat to borrow. And some fraction of the vapor released will not be captured at all. It will find the nearest cold surface, which is quite often the extraction hardware itself, and freeze onto it. What escapes that fate escapes the moon, drifting off into the thin exosphere and away permanently. There are gentler proposals. One of the more elegant would avoid digging altogether by tenting a patch of shadowed ground with reflective material and warming it with sunlight piped in from a nearby ridge, letting the vapor rise into a cold collector rather than tearing the soil apart. It is a good idea, and it requires deploying large, delicate structures across rough terrain in the dark, in a place where a crater wall blocks the line of sight to Earth and to the ridge both, so that even the radio link needs its own relay standing somewhere above. The third problem is the one that makes water the defining resource of this episode rather than merely an important one. Nothing replenishes it. Groundwater on Earth is part of a cycle. Rain falls, aquifers recharge, rivers run, and a well that is not overdrawn will still be a well in a century. Lunar polar ice is not part of any cycle. It is a balance accumulated over billions of years by processes that deliver, at present, an utterly negligible amount per year. It is a deposit. A settlement drawing on it is drawing down a fixed account, and the size of that account is genuinely uncertain, with credible estimates for the total polar inventory varying by more than a factor of 10, depending on how the deposits are modeled. Now set against that account everything a settlement wants water for, because drinking is only the beginning of the list. Water is oxygen and hydrogen for rocket propellant, which is the single largest commercial argument for being there at all. It is coolant in every thermal loop. It is the best radiation shielding material available for its mass, because hydrogen is what actually stops the dangerous particles, and water is a convenient way to carry hydrogen. It is irrigation for every crop. It is hygiene, without which a closed habitat becomes a medical problem within weeks. It is process water for chemistry and for construction. Every one of those demands draws on the same deposit, and every one of them grows as the settlement grows. The competition between them never resolves. Water used as propellant is water not available for shielding. Water held as shielding is water not available for crops. And propellant is the item that pays for the settlement, so the pressure to spend the deposit on the thing that generates revenue is permanent and structural. Then there is recycling, which is the honest answer to all of this, and which has a flaw. Orbiting stations have achieved water recovery in the high 90s as a percentage, and that is a genuine engineering achievement. It is also achieved on a narrow, well-characterized stream, in a system with no agriculture, no industrial process water, and no construction activity venting to vacuum. A settlement recycling at 90% loses a tenth of its water every time it goes round the loop. At 98%, it loses a 50th. Neither number is zero, and every percentage point short of 100 converts directly into an import mass that scales with population and with time. That is the same structural shape as the buffer gas bill from the last part, and it will not be the last time this shape appears tonight. There is one more cost to the deposit, and it is not measured in tons. Those shadowed floors are the only intact record of how volatile material was delivered to the inner solar system. The ice layered there preserves a chemical history of comets and asteroids arriving over billions of years, undisturbed, unmixed, uncontaminated, in the only cold trap close enough for us to sample. It is an archive, and it is the sort of archive that cannot be regenerated once it has been dug up, heated and breathed. There is at present no framework anywhere for deciding between a settlement that needs the water and a question about the origin of Earth's oceans that only that ice can answer. The two uses are simply incompatible, and whoever arrives first will decide. So the second entry in the ledger reads like the first, in a slightly different key. There is water on the moon. It is genuinely there, and it is genuinely enough to begin with. It sits at the bottom of the coldest holes in the neighborhood, bound into frozen ground, in a quantity nobody can state with confidence, and it does not come back. A settlement can drink from it, grow crops with it, hide behind it, and fly home on it, and every one of those choices spends a balance that took 2 billion years to accumulate and will not be topped up. A well implies a future. A mine implies an end. Everything about lunar water behaves like the second one. Part 4. The handful of ridges. The same upright axis that creates the cold traps creates the only genuinely favorable feature the moon has to offer, and it sits directly beside them. Because the sun never climbs high near the poles and never sets far below the horizon either, there are high points up there where it simply circles. On a few ridges and crater rims, direct sunlight falls for 80 to 90% of the year, and the dark intervals last days rather than a fortnight. That distinction is enormous in engineering terms. A power system sized to carry a base through 14.5 days of night is a very different machine from one sized to carry it through 3. The mass difference runs into many tons, and mass on the moon is the currency everything else is priced in. The hardware that exploits this looks unfamiliar. Solar arrays at a polar site are not laid flat to face an overhead sun. They stand vertically, like sails, tracking the sun around the horizon through the month, and they are often mounted on towers to lift them above the local terrain and out of the shadow of the next ridge along. Standing upright at grazing incidents means they present their full face to any dust lofted by nearby activity, which is a problem we will come back to. And the dark intervals, short as they are, still have to be carried by stored energy or by a reactor, and storage is always sized for the longest expected outage rather than the average one. A site that is dark for 3 days twice a year needs 3 days of storage all year round. So those ridges are the good ground. They are also, and this is the part that decides the shape of lunar settlement for the next century, extremely few. There is no location on the moon with perfect illumination. Not one. The best sites hover in the high 80s, and the number of places above 80% is a scattering of ridges and rims at both poles, each of them at most a few hundred meters to a few kilometers across. Several are on slopes. Most are adjacent to the same permanently shadowed craters that hold the ice, which is exactly why they matter. A settlement needs continuous power and access to volatiles, and only a handful of places on an entire world offer both within a practical haul. The result is that every serious architecture from every serious agency converges on the same few square kilometers of a world the size of 2 continents. That convergence is the constraint. It is not a technical problem at all. It is a geometry problem with political consequences. Consider what happens when several operators want the same ridge. Landing throws material. A descending vehicle's exhaust strikes loose soil and accelerates it outward at velocities that, in many cases, exceed the speed needed to leave the moon entirely. Some of that material never comes down. The rest travels ballistically, unslowed by any air, in flat trajectories that can carry resolvable particles hundreds of kilometers across the surface. Anything in line of sight of a landing is sandblasted. On a normal world, distance and atmosphere solve this. Here there is no atmosphere, the horizon is close, and every operator needs the same ridge. The recommended separations between landing zones and sensitive hardware run to many kilometers, which on a site measured in hundreds of meters is not a separation at all. It is an admission that the site can only host one operator unless everyone agrees on approach corridors, pad locations, and traffic schedules in advance. Pads themselves need to be prepared, sintered or paved, because an unimproved patch of ground excavates itself beneath a vehicle and grows more dangerous with every landing. The plume digs a shallow crater directly under the engines, and the second landing on that spot arrives on uneven ground that the first landing made. Preparing a pad is therefore not an improvement to be made later. It is a prerequisite for using the site more than a few times, and it has to be built by machines that themselves arrived by landing there. Beneath all of that sits an unsettled legal position. The governing treaties forbid any nation from claiming a celestial body, and they do not prohibit occupying a piece of ground and using it. So priority is established in practice by arrival, and by the safety zones an operator declares around its own equipment. Those zones function as claims without being claims. There is no mechanism anywhere for arbitrating two overlapping declarations, and the total number of viable sites is small enough that the question becomes real within a single generation rather than in some distant century. A site with superb illumination and no shadowed crater nearby is worth much less than it sounds, because the power has nothing to work on. A site with rich ice and no illumination is worse still, because the work has no power. It is the pairing that is scarce, not either half of it, and the pairing exists in the low tens across an entire world. The physical character of these places deserves a moment, because they are unlike anywhere else on the moon. At the equator, the sun stands overhead and the ground reaches 120 degrees. At a polar ridge, the sun is always low, always grazing, and the surface never gets anything like that hot. The thermal environment is far gentler, which is another reason those sites are the ones everyone wants. But that same grazing light produces a landscape of extraordinary contrast. Shadows are hundreds of meters long and razor-edged, and they sweep slowly around as the sun circles. Anything taller than a person throws a black stripe across the ground far longer than itself. The difference in brightness between lit rock and shadowed rock exceeds what most cameras can capture in a single frame, and what a human eye can accommodate at once. Navigating such terrain by sight is genuinely difficult, and the terrain itself is steep, ancient, and heavily cratered. The flat ground available at any given illuminated site, once slopes and craters and boulder fields are subtracted, is measured in hectares, not square kilometers. A settlement's habitats, its pads, its solar arrays, its radiators, its farm modules, and its storage all have to fit into an area smaller than a large farm, on a slope, beside a cliff, next to the only ice for 1,000 kilometers. Communication adds its own quiet complication. From the equator, Earth stands high in the sky and stays there. From a polar site, Earth sits low on the horizon, and local terrain can block it entirely for long stretches. Relay satellites solve this, and the Moon's gravity field is unusually lumpy, with dense concentrations of mass buried beneath the old impact basins that tug at anything in orbit. Only a small number of orbits are stable enough to hold a relay for years without constant correction. So the good orbits are scarce in precisely the same way the good ridges are scarce, and for the same underlying reason. The Moon is not a large world that happens to have some good spots. It is a world with a very small number of usable places and an enormous amount of ground that no one will ever want. There is one more layer to the scarcity, and it is easy to miss. The ridge is valuable because of what is next to it. The crater is valuable because of what is in it. And the two are typically within a few kilometers of each other, which sounds convenient right up until anyone has to build a road between them. That few kilometers crosses some of the roughest terrain on the Moon, over slopes whose stability nobody has characterized, on ground that has been shaken and reworked by impacts for 4 billion years and whose bearing strength varies from step to step. So the third entry in the ledger is not a material at all. It is a place. The Moon supplies, in the whole of its surface, perhaps a dozen or two locations where a permanent settlement makes physical sense, and it supplies them clustered, cramped, contested, and undivided by any authority. Everything else in this audit assumes a site. This is the part where we notice how few of them there are. Part 5. The dust that never rounds off. Lunar dust is the hazard most often mentioned and most often misunderstood. It is not a problem because it is dirty. It is a problem because of how it was made and because of what that leaves behind. On Earth, every grain of sand has been through a process of gentling. Water tumbles it. Wind rolls it against its neighbors. Over enough time, the edges come off and the surface is round, and the chemistry at those surfaces settles into something inert. There is no water on the Moon and no wind, and so nothing has ever gentled a single grain of lunar soil. Every particle up there was made by an impact, and impacts do only two things. They shatter rock into splinters, or they melt it and weld the fragments back together into a jagged, glassy aggregate. That second product, the welded aggregate, can make up a quarter to half of a mature soil by mass. The population of particles that results is angular, splintered, glass-sharp, and at the fine end, genuinely needle-like. A large share of it is finer than 20 micrometers, well below the width of a human hair, and a small but significant fraction is smaller than a wavelength of visible light. Two further properties make the fine fraction uniquely destructive, and neither has any terrestrial equivalent. The first is iron. Micrometeoroid impacts vaporize rock, and the solar wind chemically reduces it, and the result is vanishingly small particles of metallic iron embedded throughout the glass. This makes lunar dust magnetic, which is occasionally useful. It also makes it strongly absorbent of microwaves, which is genuinely useful, because it means the soil can be sintered into a hard paving surface using microwave energy alone. And it makes the freshly broken grain surfaces chemically reactive in a way terrestrial dust never is. On Earth, a newly fractured mineral surface passivates within moments because it meets air and water and settles down. In vacuum, there is nothing to settle it. Those surfaces stay activated, waiting, sometimes for a very long time, until they encounter moisture. In practice, the first moisture they encounter is lung tissue. The second property is charge. The sunlit surface of the Moon charges positive under ultraviolet light, which knocks electrons off it. The night side charges negative under the electron flux flowing past. And near the line between them, where day meets night, the difference generates electric fields strong enough to lift the smallest grains off the ground without any wind at all. Dust on the Moon moves by itself. There is an old observation tied to that charge, and it remains unresolved. Crews in orbit around the Moon reported a faint glow along the horizon just before sunrise, a soft band of light above the surface, where there should have been nothing but black. The natural explanation was dust, lifted electrostatically and hanging in a thin haze high above the ground. Later searches from orbit, looking specifically for that population of grains, did not find it in the quantity the glow implied. So the effect is real, and its scale is not settled, which is a fair summary of a great deal of what we know about how this material behaves. One more property matters for anything that has to be assembled or maintained. Dust sticks harder in vacuum than it does in air. On Earth, a microscopically thin film of adsorbed water sits on every surface and keeps the contact area between a grain and a wall small. In vacuum, there is no film. The grain meets clean material directly, and the electrostatic and molecular forces act across the whole contact patch. Lunar dust does not rest on a surface. It bonds to it. For a mission lasting a season, all of this is a nuisance with known workarounds. For a settlement that has to last decades, it becomes the single largest maintenance driver, because the dust does not accumulate in a straight line, and it never leaves. The record from the surface excursions we have already made is instructive, and those visits lasted days. Suits came back visibly abraded, worn through outer layers at the knees. Joint bearings at wrist and shoulder degraded from embedded grit within a handful of outings. Sample container seals leaked because dust had worked into the sealing surfaces. Everything that had been white was grey, and the dust that came inside on the suits became airborne in the reduced gravity of the cabin and stayed suspended far longer than it would on Earth, which turns an exterior problem into an interior one at every single airlock cycle. Returning crews described a smell like spent gunpowder when the material met cabin air, most likely those activated grain surfaces finally reacting with humidity. The health picture is not exotic. It is the familiar picture of occupational dust disease, of fine, sharp reactive particles reaching the deepest parts of the lung and staying there. What makes it different is that the exposure is chronic, unavoidable, and spread across a working lifetime rather than concentrated into an incident. Mitigations exist, and every one of them is partial. Suit ports that dock the suit to the outside of the habitat, so the dusty surface never comes in at all. Electrodynamic shields that run traveling electric fields across a surface to sweep particles off it. Magnetic separation, which works precisely because of the iron. Sintered paving to stop dust being raised near the base in the first place. None of them is a solution, and cleaning by any mechanical means removes some of the dust while driving the rest deeper into whatever it is embedded in. The sharpest grains are always the ones that persist. The quietest and most serious version of the problem is thermal, and it will matter enormously later tonight. Radiators and solar panels are optical surfaces. Their entire function depends on how they interact with light. A radiator works by being a good emitter of infrared and a poor absorber of sunlight. A solar panel works by being a good absorber across the visible band. Dust settling on either one degrades exactly the property it was built for. On a radiator, a thin coating of grey soil raises how much sunlight the surface takes in, while doing almost nothing for how much heat it can throw out. The panel that was supposed to shed heat begins collecting it instead. And because there is no rain to wash it and no wind to blow it clear, that degradation is one-directional. It begins the day the hardware is set down and continues for as long as anything nearby moves. Every rover traverses lofts material. Every landing lofts material. Every excavation, every construction operation, every footstep contributes to a slow grey accumulation on every optical surface downrange. So a settlement's ability to generate power and its ability to reject heat both decay continuously on a schedule set by how busy the settlement is. That is the shape of it. The busier the place gets, the faster its two most fundamental utilities degrade, and the busier a place gets is exactly the measure of whether it is succeeding. There is one further complication for anyone hoping to see through it. With no atmosphere to scatter light, the lunar sky is black at all hours, and a dusted visor or a dusted camera lens sits between a bright surface and that blackness. The grains catch the sunlight and glare, and the glare has nothing to blend into. A film of dust that would be a mild inconvenience on Earth becomes, against a black sky, a wall of scattered light. The dust is also patient. Impacts continue to turn the top layer of soil over, slowly, at a rate measured in millimeters across millions of years, so the surface is not quite static. But nothing there rounds off. Nothing weathers smooth. The grains that will be working their way into a habitat's bearings a century from now are the same grains that were made 2 billion years ago, and they are exactly as sharp as they were on the day they formed. Older soils are worse, not better, because a longer history of impacts means a finer grain population and a higher fraction of the welded glassy material. The polar ground that every settlement wants to build on is among the oldest ground the Moon has. Part 6. Machinery aging in a place with no factories. A settlement is not only a population of people, it is also a population of machines, and machine populations have demographics. Everything installed on the Moon begins aging the moment it is set down, and the environment there supplies a specific and unusual set of ways to age. The first is thermal cycling. Away from the polar ridges, hardware swings through roughly 250 degrees twice a month, from around 120 degrees in full sun to below -130 in shadow. Every one of those swings expands and contracts every joint between dissimilar materials, and the whole point of a complex machine is that it is made of dissimilar materials. Solder joints fatigue. Adhesive bonds creep. Cable insulation stiffens and cracks. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. None of it fails on the first cycle or the 10th, and all of it accumulates damage on a schedule measured in cycles rather than in years. The Moon delivers about 25 of those cycles a year to anything left exposed. The second mechanism is the vacuum itself, and it does something to metal that has no equivalent in air. On Earth, every metal surface carries a thin oxide layer, formed the instant it meets the atmosphere. That layer is what keeps two pieces of metal from becoming one piece of metal when they touch. In hard vacuum, there is no oxide, and clean metal pressed against clean metal will simply diffusion bond. Atoms cross the interface and the two parts become continuous. A bearing becomes a solid lump. A hinge becomes a bracket. This is not a theoretical concern. Mechanisms have seized this way in ground testing and in flight, and the mitigations are coatings, deliberately dissimilar material pairs and designed clearances rather than any general cure. Everything soft has its own problems. Lubricants either evaporate into the vacuum or migrate away from where they were needed, and the formulations that survive are specialized, expensive, and finite. Polymers lose their plasticizers by outgassing and become brittle. Ultraviolet light and charged particles break their molecular chains from the outside inward. And the components a pressurized habitat depends on most completely, the elastomeric seals around every hatch and every window and every joint, are among the least durable materials in the whole assembly. The third mechanism is not a mechanism at all. It is an absence, and it is the one that decides the question of permanence. There is no repair economy on the Moon. A settlement can produce oxygen, crude metal alloy, sintered paving, cast structural shapes, and shielding mass by the ton. What it cannot produce is a bearing to a specified tolerance, a gasket in a specified compound, a pump seal, a filter membrane, a sensor, a semiconductor, a pharmaceutical, or a length of wire with insulation rated for the temperature it will see. The gap between what can be made locally and what a working habitat consumes is not a gap in scale. It is a gap in kind. That is worth sitting with, because it is the least intuitive fact in this entire audit. A modern industrial product is the output of a supply chain drawing on dozens of elements from dozens of places, refined to purities that require entire specialized industries of their own. A single electric motor needs copper of a certain purity, magnetic material with rare earth content, a polymer insulation system, a lubricant, a bearing steel and a housing, and each of those is itself the end of a long chain. The moon is one place with a small number of elements, all of them dispersed and none of them concentrated. So the true measure of a settlement's independence is not its power output or its oxygen plant. It is its spares inventory. Every component that can fail must exist either as a stocked spare or as an accepted risk, and the number of distinct part numbers in a habitat runs into the tens of thousands. Stocking deeply costs mass on every launch. Stocking shallowly costs availability when something breaks. Neither choice produces independence, because both are denominated in imports, and the inventory has to grow every time the settlement does. Printing helps at the margins, and only at the margins. A machine that builds objects layer by layer can turn out brackets, housings, tool handles, and simple replacement shapes from local metal or from polymer feedstock, and that genuinely reduces the inventory of dumb parts. But the feedstock for anything precise is imported. The print heads and lasers are themselves consumables, and the finished parts have material properties that are good rather than specified. Printing solves the problem of shapes. It does not touch the problem of materials. There is a second constraint that has nothing to do with hardware. Repair depends on who is standing there. A settlement of 30 people cannot hold the range of specializations that a terrestrial industrial site takes entirely for granted, where a failure summons someone who has spent 20 years on that exact class of equipment. On the moon, capability is bounded by headcount as much as by inventory, and headcount is bounded by everything else in this audit. Automation shifts the burden without removing it, because every robot is another population of wear-limited components with its own spares list. The pressure shell sits apart from all of this, because it is the one component that must never fail. Hulls are therefore heavily overbuilt, and every place where something crosses them becomes a separately tracked liability for the life of the settlement. Every window, every hatch, every cable pass-through, every plumbing run, every instrument port. A habitat's risk is concentrated at its holes, and every figure above assumes ordinary operation. A single unplanned event, a hard landing nearby, a pressure loss, a fire in a sealed volume, consumes spares at a rate that no inventory plan has ever anticipated, and the resupply that would replace them is a launch campaign away. Long experience with orbiting stations has taught one consistent lesson about this. The parts that fail are almost never the parts predicted to fail. The value of an inventory therefore lies in its breadth rather than its depth, which is precisely the expensive direction. The systems that break most often are entirely unglamorous. They are the ones that move fluids and gases. Pumps, valves, fans, filters, seals, and rotating machinery of every kind. All of them wear limited, all of them needed continuously, none of them optional. A habitat is at bottom a plumbing system with people living inside it, and plumbing wears out. Electronics fail along two separate paths. There is cumulative dose damage, which degrades performance slowly as radiation accumulates in the semiconductor structure, and there is the single energetic particle that passes through a junction and flips a bit or destroys it outright. Hardening against both is possible and comes at a cost in capability, which is why radiation-tolerant processors typically run generations behind ordinary commercial parts. A lunar settlement, therefore, operates computers that are simultaneously its most critical systems and its least advanced ones. Layered over all of it is the dust from the last part, which accelerates every wear mechanism listed here. Abrasive particles in a bearing, on a seal face, in a valve seat. The dust problem and the aging problem do not add together. They multiply. And there are the impacts. Micrometeoroids arrive continuously at average speeds around 20 kilometers per second, which means even a grain of sand carries an extraordinary amount of energy for its mass. Thin-walled structures defend against this with spaced bumper shields, a sacrificial outer layer that breaks the impactor into a spray before it can reach the pressure wall. It works well. It also means the outer skin of every habitat is slowly being consumed by design. Underneath everything, the moon itself moves a little. It is contracting slowly as its interior cools, and the surface has wrinkled into low ridges where the crust has been pushed together. Some of the youngest of those wrinkles cluster near the South Pole, in exactly the region every architecture wants to occupy. Shallow quakes have been recorded at magnitudes above 5, and because the crust there is cold and bone dry, it does not damp the shaking the way wet terrestrial rock does. It rings, for tens of minutes at a time, quietly, in a place where nothing else moves at all. Part 7. Bodies adapting to the wrong world. It is worth pausing here, at the middle of the night, to set down what the ledger holds so far. The air can be half-made, and never wholly made, because the inert part that fills the lungs is the part the moon does not have. The water is real and behaves like a mine rather than a well, a fixed balance accumulated over 2 billion years that does not refill. The places where both power and ice are available number in the low tens across an entire world, and they are small, steep, crowded, and unassigned. The soil that covers everything is sharp, reactive, and electrically restless, and it degrades the settlement's power and its cooling continuously, at a rate set by how busy the settlement is. And the machinery ages under a temperature swing twice a month, in a vacuum that welds clean metal together, with no factory anywhere within 250,000 miles that could make a replacement part. All of that concerns the settlement as an object. Everything from here concerns the people inside it, and the difficulty changes character entirely. It stops being a question of engineering and becomes a question about evidence that does not exist. Human physiology has been studied carefully at 1 gravity, which is Earth, and studied carefully at effectively no gravity, which is orbit. Between those 2 values there is nothing at all. No person has ever lived for a long period at 1/6 of their normal weight. No animal has either, in any study of meaningful duration. Every projection about long-term health on the moon is an interpolation drawn between 2 points, and a line drawn between 2 points cannot tell anyone whether the curve between them is straight, gently sloped, or shaped like a step with a drop on one side. What is known from orbit is not encouraging. Weight-bearing bone demineralizes at roughly 1 to 1.5% per month in free fall, concentrated in the hip and the lower spine, and it does not fully recover on return even after years. Muscle mass declines. Cardiovascular conditioning declines. Fluid shifts toward the head produce a syndrome of swelling at the optic disc, flattening of the back of the eye, and changes in vision that persist in some people long after they land. The immune system behaves differently. Dormant viruses reactivate. Wounds heal more slowly. 1/6 of Earth's gravity may prevent nearly all of that. It may prevent very little of it. There is a reasonable argument that even a small constant load is enough to trigger the biological signals that maintain bone, and there is an equally reasonable argument that the body responds to the load it actually experiences and will demineralize to match. The honest position is that nobody knows. And the experiment that would answer the question is the settlement itself, gathering one data point per person per year, which is the slowest and most expensive clinical trial ever proposed. Radiation runs alongside all of this, and it is far better characterized. With no atmosphere overhead and no global magnetic field, the lunar surface receives the full flux of galactic cosmic rays, plus whatever the sun sends. The annual dose is a few hundred millisieverts against a terrestrial background of a few. But the number understates the problem, because cosmic rays are not ordinary radiation. A substantial part of the flux is bare atomic nuclei of heavy elements, moving near the speed of light, and each one deposits energy along a dense track as it passes through tissue. A cell hit by such a track is not damaged in the diffuse way a medical X-ray damages tissue. It is cut through. What that pattern of damage does to the central nervous system over decades is an open research question, not a settled one. Career limits are set by acceptable lifetime cancer risk, and on the unshielded lunar surface, those limits are reached in a period measured in months to a couple of years, not decades. Shielding works, and works very well, and the material is free. Around 2 meters of piled regolith removes most of the cosmic ray dose. Hydrogen-rich material such as water or polyethylene does the same job with considerably less mass, because hydrogen is what actually breaks up the incoming particles. But shielding introduces its own strange complication. When a high-energy nucleus strikes dense material, it does not simply stop. It shatters, producing a shower of secondary particles, many of them neutrons, and those secondaries carry on into whatever lies beyond. At certain intermediate shield thicknesses, the dose on the inside can be higher than with no shield at all. A partial shield can be worse than none, which is a deeply unhelpful property for anyone building incrementally. The sun inverts the risk on an 11-year rhythm. At solar maximum, the sun's magnetic influence extends outward and partly excludes galactic cosmic rays, so the chronic background dose falls. In the same period, the probability rises sharply of a solar particle event, a sudden flood of energetic protons that must be survived inside heavy shielding. So the quiet years carry the higher steady dose, and the active years carry the higher acute risk, and a settlement cannot choose which era it exists in. The most protective arrangement available is also the least appealing one. Burying a habitat under meters of soil, or setting it inside one of the enormous lava tubes that run beneath the ancient plains, hundreds of meters wide and roofed by solid rock, removes almost the entire radiation problem in a single decision. It also removes every window, every view, and every direct sense of where anyone is. The safest place on the moon is a sealed volume underground with nothing to look at, and the people inside it would spend most of their lives there. Shelter geometry then constrains the entire layout of a base. Every person working on the surface must be able to reach heavy shielding within the warning time of an event, which is tens of minutes at best. That single requirement sets the maximum radius of surface operations around any settlement, and the radius is small. Medicine on the moon operates under its own restrictions. Pharmaceuticals degrade faster after radiation exposure in transit and in storage, so a stockpile is a consumable with a shelf life rather than an asset. Surgical capability is limited by mass and by who happens to be present. And the countermeasure that keeps orbiting crews functional, roughly 2 hours a day of resistance and cardiovascular exercise on heavy equipment, has no established equivalent at 1/6 gravity, because nobody knows what regime would be sufficient. That makes crew time budgeting a matter of estimate rather than plan. The ordinary business of moving around is stranger there than people expect. Walking at 1/6 gravity does not work well, because an ordinary stride cannot generate enough force against the ground, and the natural result is a loping bounce that early crews adopted within minutes. Falling is slower and gentler, which sounds safer and is not, because the person falling is inside a pressure vessel whose integrity matters far more than their balance. Distance is misjudged constantly because there is no haze to soften anything far away and no familiar object anywhere to set the scale, and the horizon itself sits only a couple of kilometers off across level ground. Then there is sleep, which in a place with no natural day is entirely a matter of lighting discipline. Circadian drift is a persistent and well-documented problem in long-duration crews even with careful scheduling, and on a world where the sun takes a month to cross the sky, the only thing keeping a body on a 24-hour rhythm is the decision to keep it there. There is one further consequence, and it is the quietest thing in this part. Adaptation is a one-way door. A body that spends years at 1/6 gravity does not simply pause. It respecifies itself. Bone reshapes for the load it feels. The cardiovascular system adapts to a shorter effective column of blood. The vestibular system recalibrates. Every one of those adaptations makes return to Earth harder, and at some duration, which nobody can currently state, return stops being difficult and becomes medically inadvisable. So a settlement acquires, gradually and without anyone deciding it, a population that cannot leave. Not because it is confined, not because anything has gone wrong, simply because the bodies of the people living there have quietly respecified themselves for the world they are standing on, while the world they came from carries on turning, in full view, in the same patch of sky, 6 times too heavy to visit. Part 8. The question of children. Every argument for settlement, rather than occupation, eventually arrives at the same place. A settlement is not a settlement until people are born in it. And it is here that the absence of evidence stops being an inconvenience and becomes the central unknown of the whole enterprise. Human development is a gravity-dependent process from long before birth. The vestibular system, the small arrangement of fluid-filled canals in the inner ear that tells a body which way is down, calibrates itself in early life against a constant downward acceleration. The skeleton lays down mineral in response to load, and the load is weight. Muscle patterning, the curve of the spine, the tone of the cardiovascular system, and even the growth of the inner ear itself all develop against a background of one gravity. Not one of them has ever developed against 1/6 of it. Before any of that, there is gestation. The distribution of fluid within a womb, the settling of an embryo against a wall, the mechanics of birth, the mechanics of nursing, all of it evolved under a particular weight and has never been tested under any other. There is limited animal work in free fall, showing altered bone development, changed reflexes and differences in early motor learning, and there is essentially nothing at partial gravity. What exists is neither long enough nor large enough to settle any question that matters. Radiation compounds it. A developing nervous system is considerably more radiation sensitive than an adult one, and the exposure limits that apply to children are stricter than occupational limits by a wide margin. So a nursery on the moon is not a room with a cot in it. It is a shielded volume beneath meters of piled soil, with rules about how long a child may spend in the less protected parts of the settlement, and how often, and under what conditions. Childhood on the moon would be by necessity, an indoor childhood spent mostly underground. The shielding requirement has an unhappy geometry to it. The most protected volume in any settlement is the one buried deepest, with the most mass overhead and the fewest openings, which means the safest place for a child is also the least stimulating one. Every window is a thinning of the shield. Every view outward is a decision to accept some dose in exchange for something to look at. On a world where the landscape is grey and unchanging and the sky is permanently black, the trade is not even a generous one. There would be no reference standards to measure such a child against. Every growth chart in existence describes children who grew up at 1 gravity. A lunar pediatrician would be watching a process nobody has ever observed, without any way of knowing whether what they were seeing was healthy development in a new environment or the early stage of something going wrong. And then there is the quietest consequence of all, and it is not medical at all in the end. A child who grows to adulthood at 1/6 gravity may have a skeleton and a cardiovascular system that cannot tolerate Earth. Not immediately, perhaps not with any amount of training, possibly not at all. The likely picture is someone taller than their parents, with less dense bone and a circulatory system tuned to a shorter column of blood. Such a person's ancestral world would be a place they could see in the sky every single day of their life and never once visit. And the sky above a lunar settlement holds Earth in a fixed position. The moon keeps one face turned toward us, so from the near side Earth does not rise and does not set. It hangs in the same patch of black, wobbling very slightly, going through its phases, 4 times wider than the moon appears from here, and bright enough to cast shadows across the ground at night. It is not a thing that comes and goes. It is a fixed feature of the landscape, like a mountain, and it is unreachable. The arithmetic of population runs underneath the biology and is no simpler. A genuinely self-sustaining human population needs a founding group large enough to avoid genetic bottlenecking. The numbers usually discussed for long-term genetic health, as opposed to short-term survival, run to thousands rather than dozens. And every additional person in a lunar settlement adds pressurized volume to fill with imported buffer gas, water demand drawn from a finite deposit, crop area under electric light, waste heat to reject, spares to consume, and a lifetime radiation budget to spend. Population growth on the moon is not merely a demographic matter. It is an import problem, denominated in exactly the columns the moon cannot fill. There is a way to soften the mass side of that requirement, and it comes with questions of its own. Genetic diversity does not have to arrive as people. Stored genetic material weighs almost nothing compared with the bodies that would otherwise carry it, and a small founding population could, in principle, maintain the diversity of a much larger one that way. The engineering is straightforward. Everything else about it is not, and it remains entirely open. A community of a few dozen also has a social shape with almost no terrestrial precedent. The closest analogues are the smallest and most isolated human settlements on Earth, and every one of them depends on periodic contact with a larger population, for trade, for medicine, for marriage, and for the ordinary relief of seeing an unfamiliar face. A lunar settlement would have contact in the form of a screen and a delay of a second or so. It would not have a rival. A child growing up there would know every adult they had ever met, would have a handful of peers at most, and would learn about the world their species comes from entirely at second hand, from people describing weather they would never feel. Medical capability sits in the same bind. Pregnancy and childbirth require surgical facilities, blood products, anesthesia, and neonatal support. All of it is mass expensive, none of it can be improvised, and all of it must be present before it is needed rather than after. which leaves a decision with a very unusual shape. The choice to attempt the first birth on another world is irreversible in a way that no other decision in the program is. A habitat can be abandoned. A mine can be closed. A crew can be brought home. A child cannot be unborn and cannot be sent to a world their body may not tolerate. That decision would have to be taken with less physiological evidence than is normally required to license a mild medication, and no amount of preliminary work can supply the missing evidence, because the only experiment that produces it is the decision itself. There is an alternative, and it is entirely workable, which is what makes it so revealing. A settlement can simply decline the question. It can rotate its population instead, exchanging people on a schedule of months or years, keeping everyone inside their dose limits and their bone loss within recoverable bounds, and never asking anyone to stay long enough for the one-way door to close behind them. That arrangement is stable. It is sustainable indefinitely, in principle. And it is, precisely and by definition, an outpost. So this is the trap in its clearest form. The arrangement that works is the one that never becomes permanent. The arrangement that would be permanent is the one nobody has the evidence to authorize, and the evidence can only be gathered by people who have already committed to it. There may be intermediate answers. A centrifuge inside a habitat could spin a sleeping area or a nursery up to a higher effective weight for part of each day, which is a genuinely promising idea and requires a radius large enough that the rotation does not disorient anyone, along with the power and the mass to turn it. Perhaps that is where the answer lies. Perhaps a lunar child would sleep each night at something closer to Earth's pull and walk out in the morning into 1/6 of it and grow up somewhere between the two. Nobody knows. That is the honest end of this part, and it is worth letting it be honest. Of all the entries in this ledger, this is the only one where the missing quantity is not a resource, or a place, or a component. It is simply information that does not exist yet, and there is exactly one way to obtain it. Part 9. Food as manufactured output. Food on the moon is not grown in the sense the word usually carries. It is manufactured out of imported carbon and imported nitrogen using electricity inside a shielded volume under lamps. The energy accounting is the first thing that surprises people. Sunlight at the lunar surface is free, abundant, and unfiltered by any atmosphere, and it is very nearly useless for agriculture because crops have to live under shielding along with everyone else. A greenhouse with a transparent roof on the lunar surface is a greenhouse full of cosmic rays and solar protons, and the plants inside it would be sterilized by the first serious particle event. So the light has to be electrical, generated by a reactor or an array outside and delivered to the leaves through lamps. Photosynthesis is not efficient. Only a small percentage of the light energy falling on a leaf ends up stored as biomass, and only a fraction of that biomass is edible. Tuning the lamps to the specific bands that chlorophyll absorbs helps considerably, and it is the reason crop lighting has moved toward narrow spectra rather than white light. Even so, crop illumination remains the single largest continuous electrical load in a lunar settlement, larger than life support, larger than the oxygen plant, larger than anything except heavy industry. The area required is substantial. Feeding one adult a complete diet takes something in the range of a few tens of square meters of continuously cropped surface, and every one of those square meters is pressurized, shielded, lit, irrigated, temperature-controlled, monitored, and staffed. Multiply by a population, and the farm becomes the largest structure in the settlement by a wide margin, and the most demanding to build. The composition problem comes next, and it returns us directly to the trap. A crop takes up nitrogen, phosphorus, potassium, and a long list of trace elements, and without them, it does not produce. Nitrogen has to be imported, as we established. Phosphorus does exist in lunar rock, at low concentration, locked into minerals that require real chemical processing to release. And every gram of every nutrient that leaves the loop must be replaced. So the nutrient cycle has to be closed almost perfectly, which means human waste, inedible plant material, and every other organic stream has to be recovered, broken down, and remineralized into forms roots can take up. Nothing can be discarded. There is nowhere to discard it to, and no ability to replace it. Carbon dioxide is its own quiet arithmetic. The crops need it, the crew produces it, and the two numbers do not balance. A group of people does not exhale nearly enough carbon dioxide to feed the plants that feed them, because most of the carbon in the food ends up in bodies and in waste rather than back in the air. So supplemental carbon has to come from stores, and stores come from Earth. Then there is the biology, which is the part that behaves least like engineering. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Part of that community is necessary and welcome in the root zone and in the waste processing beds. Part of it is not. And a pathogen that establishes itself in a closed farm has no natural predators, no seasonal dieback, no quarantine possible beyond the module wall, and nowhere else to be. Fungal contamination is the most commonly reported problem in closed growth systems on Earth, because fungal spores are everywhere, tough, and nearly impossible to eliminate once established. A crop disease in a settlement with one growing volume is not a bad season. It is a supply crisis with a delivery time measured in months, and the only buffer against it is stored food, which means the true measure of an agricultural system is not its yield at all. It is the size of the reserve standing behind it. Plants also poison their own air, slowly, in a sealed volume. Growing crops release a steady stream of volatile organic compounds, and on Earth, those simply disperse into a sky that has room for them. In a closed module they accumulate, and at high enough concentrations they begin to damage the plants producing them. So a lunar farm needs scrubbing systems tuned to the particular chemistry of its particular crop mix, sitting alongside the scrubbers that handle the crew's own contaminants, each of them consuming filter media that arrives from somewhere else. Trace elements drift as well, in ways that are difficult to predict in a system this small. In a terrestrial field, soil buffers everything. Deficiencies develop over seasons and can be corrected from a bag. In a closed loop of a few hundred square meters, an element can deplete or accumulate over a handful of cycles, and either condition will show up first as a crop that quietly underperforms for reasons nobody can immediately identify. Continuous chemical monitoring is therefore not an optional refinement. It is the only way to see the problem before the harvest does. And the nitrogen, once imported, has to be kept in a usable form. Plants cannot take up nitrogen gas. It must be fixed, biologically or chemically, into compounds roots can absorb, and then recovered again from waste after every harvest. That is a processing plant of its own, with its own power draw, its own maintenance schedule, and its own ways of failing, sitting between the imported gas and the food. It is worth noting how far this is from terrestrial indoor farming, which is often cited as the proof that all of this works. Those facilities achieve genuinely impressive yields per square meter. They do it with abundant grid power, municipal water, carbon dioxide delivered by the tanker, nutrients bought by the sack, and an atmosphere that comes free with the building. None of their economics has ever had to include the cost of manufacturing the air. Even the seeds are a consumable. Seed viability declines under radiation exposure during transit and in storage, so a seed bank is not a permanent asset, but a stock with a shelf life, needing replacement from a planet that has plenty of seeds and a long way to send them. The crops themselves would behave strangely, in ways that are only partly understood. At 1/6 gravity, water moves differently through soil and substrate, because capillary action stays strong while drainage weakens. Roots orient partly by gravity, and that cue is diminished. Most importantly, the air around a leaf does not clear itself. On Earth, a leaf warms slightly in light. The air against it rises, and fresh air carrying carbon dioxide moves in behind it, all of it driven by buoyancy. In weak gravity, that convection is feeble, so a still pocket of depleted air forms against the leaf surface and stays there. A lunar farm therefore needs constant forced airflow, simply to let the plants breathe, and that airflow is another fan, another motor, another wear-limited component, running continuously in every module. The menu that results from all these constraints is narrow. The crops that make sense are the ones with short cycles, high edible fractions, tolerance of artificial light, and efficient use of area. Leafy vegetables are marvelously efficient per square meter and supply almost no calories. The staples that actually feed people, the grains and the starchy roots, need far more area per calorie, and they are what drives the size of the farm. Protein is the hardest category of all, because legumes are area expensive and animals multiply every burden in the closed loop several times over. Most serious architectures either accept imported protein or accept an unusual diet, and the unusual diet has a cost that is easy to underestimate. In isolated crews, food carries a psychological weight out of all proportion to its nutrition, and the monotony of a short crop list is a documented factor in long-duration morale. So the entry in the ledger reads like all the others, in yet another key. The moon can supply the volume, the shielding mass, the water for a while, and the electricity. It cannot supply the carbon that the food is built from, nor the nitrogen the plants need to build it, nor the phosphorus without real industry, nor a replacement seed stock, nor a way to flush a pathogen out of a sealed room. A lunar farm is a beautiful piece of engineering and a permanent import line, and like every other line in this audit, it grows longer with every person the settlement adds. Part 10. Heat, the thing that cannot be thrown away. The constraint that eventually caps the size of any lunar settlement is not air, or water, or food, or power. It is heat, and almost nobody expects it. On Earth, waste heat disappears without anyone arranging it. Warm air rises off a radiator, and cool air slides in underneath. Water carries heat away from an engine and into a river or a cooling tower. The atmosphere and the oceans between them absorb everything industrial civilization produces, silently, for free, and the process is so automatic that it is effectively invisible. In vacuum, none of that exists. There is no air to warm, no water to carry anything, and no contact worth speaking of with the ground, because loose soil is one of the best insulators available. Every joule a settlement produces has to leave the same way starlight does, radiated as infrared from a physical surface into the sky. And how much a surface can radiate depends on two things only: its area and its temperature raised to the fourth power. Radiators are therefore large, and they grow rapidly larger as the temperature they must operate at falls. A habitat that wants to be comfortable inside is a habitat rejecting heat at a low temperature, which is the expensive end of that relationship. Then the environment makes it worse in a way that is specific to this world. At lunar noon at low latitudes, the ground reaches around 120 degrees, and the sun stands directly overhead. A radiator in that situation is trying to shed heat while being heated from above by direct sunlight and from below by a floor hotter than boiling water. Its effective sky is not cold and empty. It is a bright, hot hemisphere, and the panel that was designed to lose energy begins gaining it. The answers are all geometric. Turn the radiator's edge onto the sun. Raise them on structures above the ground. Shield them from the infrared coming off the surface. Or move to high latitude, where the sun never climbs, which is one more reason every architecture wants the same few polar ridges. None of these are free, and every one of them costs area, mass, or siting flexibility. Now consider what a growing settlement produces. Life support runs continuously. Lighting runs continuously. Crop illumination, which we established is the largest single load in the place, converts electricity into light and then almost all of that light into heat. Oxygen extraction runs at high temperature. Water mining warms tons of soil to release a few liters. Regolith sintering, metal processing, and every other local industry is a thermal process. Computers concentrate heat into small volumes, and their density rises as automation grows. And the people themselves each dissipate around 100 watts, day and night, simply by being alive. All of it has to leave through radiators. So a settlement's thermal rejection capacity has to be built ahead of its activity, in large, thin, fragile surfaces that are difficult to deploy, easy to puncture, and impossible to keep clean. That last point connects directly back to the dust. A radiator's performance depends on being a poor absorber of sunlight and a good emitter of infrared. Dust settling on it degrades the first property far more than it helps the second. So the settlement's ability to shed heat decays continuously from the day it is installed, at a rate set by how much traffic crosses the ground nearby, which is another way of saying it decays fastest when the settlement is busiest. There is a genuine bright spot at the poles, and it is worth naming because so little else in this audit is generous. A radiator standing vertically at a polar site can be turned to face the permanently dark half of the sky, away from the low sun and away from the hottest ground, and in that orientation it radiates into something very close to the empty cold of deep space. The rejection conditions there are nearly ideal. It is one more entry on the list of reasons why those few ridges are worth more than the rest of the moon combined. Getting a radiator into position at all is its own difficulty. Large panels have to survive launch folded flat, then unfold on arrival, and stay flat and sealed for decades, in a vacuum, through a 200-degree temperature swing every fortnight. Deployable structures of that kind are among the more failure-prone items in any spacecraft, and here they are not a convenience. They are the component that decides how large the settlement is allowed to become. Micrometeoroids add their own slow attrition. A radiator is a network of tubes carrying fluid across a wide, flat area, which is close to the worst possible shape for something exposed to a continuous rain of high-velocity grains. The standard defense is to build many small, isolatable panels rather than a few large ones, so that a puncture loses a fraction of the capacity rather than all of it. That costs mass, plumbing, valves, and complexity, and every valve is another wear-limited component. Heat pumps offer a real improvement by raising the temperature at which heat is rejected so that a smaller surface can do the job. The catch is that a heat pump consumes power, and the power it consumes becomes heat that also has to be rejected. It is a genuine gain, and it is not a free one. Burying a habitat, which is the obvious answer to radiation, makes the thermal problem harder rather than easier. Regolith is an outstanding insulator. A meter or so beneath the surface, the temperature settles at around -20 degrees and barely notices the difference between lunar noon and lunar midnight. That stability is wonderful for protecting people and terrible for getting rid of energy, because the surrounding ground will not carry heat away at any useful rate. The same property makes the enormous lava tubes attractive as habitat sites, and means that a base inside one, once it starts producing serious power, still has to run its heat all the way to the surface and radiate it into the sky like everyone else. The surface itself has almost no thermal memory, which is why the swing is so severe. Soil that conducts heat as poorly as lunar regolith responds to sunrise within minutes at the very top, while the material a single meter below never notices that the sun came up at all. The moon is therefore two thermal environments stacked directly on top of each other, a violently cycling skin over a deeply stable interior, and a settlement has to work in both at once. The lunar night presents the mirror image of the whole problem. For 14 days at most latitudes, the environment that would not accept heat now takes it relentlessly, and a habitat that was fighting to cool itself is now fighting to stay warm. Power for that comes either from stored energy or from fission, and storing 2 weeks of continuous demand is a mass problem of a completely different order from storing a few hours of it. Fission is the compact answer, and a reactor's waste heat has to be rejected through radiators sized for its full thermal output rather than the electrical fraction that is actually useful, which means the cooling hardware for the power plant is often larger than the power plant. Suits carry a miniature version of the same dilemma. Historically, the answer was to sublimate water directly into the vacuum, which cools superbly and converts the scarcest resource on the moon into cooling that is then lost forever. Closed-loop suit cooling that does not consume water has been a design goal for decades and remains difficult because a suit has to reject heat into an environment that is sometimes hotter than the person inside it. So here is the ceiling, and it is a real one. A settlement's size is bounded by the surface area it can devote to throwing heat away, and that surface is fragile, dust-sensitive, mass-expensive to expand, and made of the one thing the moon cannot supply locally. Regolith gives mass in unlimited quantity, and mass is precisely the wrong thing for a radiator. Of everything in this ledger, heat rejection is the entry with no local material answer at all. Part 11. The distance that only looks small. The moon is the nearest world, and its nearness is the most persuasive fact about it, and the most misleading. Radio takes a little over a second to cross the gap each way. A conversation with Earth has a delay that is noticeable and entirely workable, nothing like the minutes or hours that separate us from Mars. A crude transit takes about 3 days. Compared with any other destination in the solar system, this is intimacy. It is close enough that the moon has always felt like a place we could simply go to, rather than a place we would have to reach. The nearness is genuine for information and almost entirely illusory for mass. Getting from the surface of Earth to the surface of the moon means shedding, in total, a velocity budget larger than reaching orbit around Earth. Roughly 9.5 kilometers per second to get to low orbit, and several more to leave that orbit, cross the gap, slow down, and descend. All of it is delivered by propellant that has itself been lifted out of Earth's gravity. Nothing about the moon's proximity reduces that number, because the number is not a measure of distance. It is a measure of a climb. Proximity shortens the journey and leaves the climb exactly where it was. The consequences for a settlement are specific and unromantic. A return capability is not something that exists because Earth happens to be close. It is a physical vehicle, fueled, maintained, inspected, standing on the surface in a state of readiness, consuming inventory and crew time indefinitely for an event that may never come. It can carry a crew. It cannot carry a settlement. And as the population grows, the fraction of the settlement that could be removed in any single event falls steadily, until at some size, the standing evacuation capability is a rounding error against the number of people present. The obvious answer is to make propellant locally from polar ice, which is the strongest argument for lunar industry that exists. It also draws down the same finite deposit that supplies drinking water, crop irrigation and shielding, which means that the settlement's ability to leave is in direct competition with its ability to stay. Windows to and from the moon come round often, which is a genuine advantage over the interplanetary case, where a missed opportunity can cost 2 years of waiting. But frequency is not availability. A window is only useful to someone who already has a vehicle standing ready, fueled, checked and crewed, and the standing cost of holding that readiness for years without using it is the sort of expense that quietly disappears from budgets first. Medical evacuation, on any useful timescale, is not available at all. A serious injury has to be treated where it happens, with the equipment already present and the expertise already standing there. The abort options during descent and ascent are narrow, and unlike an orbiting station, there is no possibility of a fast return from the surface at an arbitrary moment. A departure requires a window, a functioning ascent stage, propellant, and a landing site on Earth prepared to receive it. Even the pleasant fact that second or so of signal delay has a sharp edge. It is small enough for conversation and far too large for teleoperation. Trying to drive a machine remotely with 2.5 seconds between an action and its consequence is possible and exhausting, and it means surface machinery has to carry a great deal of its own autonomy. From the far side, there is no direct signal at all, and relays are required, held in the small number of orbits the moon's lumpy gravity field permits. Every rotation of personnel carries a cost that is easy to overlook. The transit itself takes place outside the protection of Earth's magnetic field, so a share of each person's lifetime radiation budget is spent simply traveling rather than working. Bringing someone home and sending someone new does not reset the settlement's exposure. It distributes it across more people and adds 2 more crossings to the total. The far side is a different world again for these purposes. From there, Earth is never visible at all, blocked permanently by the entire body of the moon. That makes it the finest location in the inner solar system for radio astronomy, shielded from every transmitter our species has ever built by 3,500 kilometers of rock. It also makes it a place where nothing can be said to Earth without a relay standing somewhere above the horizon, and where the sky holds no reminder of home whatsoever. And then there is the geometry that has no equivalent anywhere in human experience. Because the moon keeps one face turned toward us, Earth does not rise or set over a near-side settlement. It hangs in a fixed patch of black sky, in the same place at every hour of every day, for the entire duration of a human life. It moves slightly, tracing a small oval over the course of a month as the moon rocks gently on its axis, which is enough to matter for anyone planning a communication link near the edge of the visible face, and not enough to notice while standing there. It goes through phases as we go through phases for them. It is about 4 times wider in that sky than the moon appears in ours, and bright enough during the lunar night to cast shadows on the ground. So the people living there would see home continuously. Not as a bright star among other stars, the way Earth would look from anywhere else, but as a blue and white world with weather visibly moving across it, close enough to pick out the shapes of continents through a small telescope, permanently fixed above the same ridge. Analog studies from isolated terrestrial stations describe the ability to see home as a mixed comfort at best. None of them has ever combined that view with a permanent inability to reach it. The people at a polar research base can see the sky their flight will come from. The people in a lunar settlement would look up at a world they might be physiologically unable to return to, hanging motionless, always in the same spot, never any nearer. The landscape underneath that fixed Earth does nothing to relieve the strangeness. The sky is black at all times, even at noon, because there is no atmosphere to scatter sunlight into blue. Sun and stars share the same sky whenever an eye is dark, adapted enough to hold both. The horizon on level ground sits only a couple of kilometers away because the moon is small and its curve is sharp, so a rover setting out disappears over the edge of the world far sooner than instinct expects. Underneath the psychology sits the logistics, which are stranger than the 3-day transit suggests. A resupply mission takes 3 days to fly and many months to build, integrate, test, and launch, and it exists inside a manufacturing and budgetary cycle measured in years. The effective distance to Earth, for anything a settlement actually needs, is not 3 days. It is a quarter or two, and it depends entirely on decisions taken by people who are not there. There is one asymmetry in the moon's favor, and it is the reason anyone talks about lunar industry at all. Sending mass from the moon to Earth orbit is enormously cheaper than sending it the other way, because the moon's gravity is weak and there is no atmosphere to fight. A settlement could plausibly export propellant, oxygen, shielding mass, even structural material, and be paid for it. That is a real economy, and it does nothing whatsoever for the problem in this audit, because everything the settlement must import is precisely the set of things the moon cannot make. A place can be commercially successful and materially dependent at the same time. Most places are. So the distance is small in every sense except the ones that determine whether anyone can stay. Close enough to see. Close enough to talk. Close enough that help is 3 days out rather than 3 years. And separated by a climb that no amount of nearness has ever made shorter. Part 12. What independence would actually require? The audit resolves, in the end, into a single page. Independence, in the only sense that matters, means that a settlement could survive an indefinite interruption of resupply without shrinking. Not survive a delayed launch. Not survive a bad year. Survive the permanent end of deliveries and go on being what it was. Set against that standard, here is what the moon supplies and what it does not. The moon supplies generously, without limit on any human timescale, the following. Mass for shielding and for construction, in quantities beyond any conceivable need. Oxygen, effectively unlimited, at a high energy cost. Crude metal alloys as a byproduct of that oxygen extraction. Sintered paving and cast structural shapes. Silicon, in impure form. And abundant solar energy at a small number of sites. The moon supplies marginally and finitely the following. Water from cryogenic deposits that do not renew. Hydrogen for propellant from the same deposits. Traces of nitrogen, carbon and helium implanted grain by the solar wind at concentrations that make extraction a matter of moving mountains to fill a tank. And the moon does not supply, at any concentration a living settlement could use, the following. Nitrogen for atmosphere and for fertilizer. Carbon for food, for polymers, for plastics, and for every fiber and seal compound in the place. The platinum group metals and rare earth elements that catalysts, motors, magnets, and electronics depend on in small quantities and absolutely. Refined chemical feedstocks of any kind. Semiconductors. Pharmaceuticals. and precision components of any specification whatsoever. That third list is the trap, written out. The two elements a human body is largely assembled from, and the two elements a habitat's atmosphere and its agriculture are built on, are nitrogen and carbon. They are also the two elements the moon almost entirely lacks. A settlement there can quarry breathable oxygen out of the ground it stands on, in any quantity it likes, forever. And every breath its people take will still be mostly imported gas. Every calorie they eat will still be assembled from imported carbon. The world beneath their feet is nearly half oxygen by weight, and almost completely empty of the elements that make a body. There are three ways out of that, and each of them substitutes one dependency for another. The first is to keep importing from Earth. This is the current answer, and it preserves the dependency exactly. The mass required per person per year, even in an optimistic closed-loop architecture, remains in the range of a few tons. Multiply by population, multiply by decades, and the total is a number that no launch economy currently in existence could support, and that grows every time the settlement succeeds at anything. The second is to import from elsewhere in the solar system. This is more interesting than it first sounds, because the small bodies are rich in precisely what the moon lacks. Carbonaceous asteroids and comets carry water, carbon compounds and nitrogen in percentages rather than parts per million, and their gravity is so weak that lifting material off them costs almost nothing. The energy case is genuinely favorable. What it demands is an interplanetary logistics capability far beyond anything that exists, operating on timescales of years per delivery, and what it produces at the end is a lunar settlement dependent on an asteroid program instead of on a planet. The supplier changes. The dependency does not. The third is radical closure. Recycle nitrogen and carbon at 99-point-something% forever and accept that the settlement can never grow, because growth requires new atmosphere for new volume and new biomass for new people. No integrated life support system has ever demonstrated closure much above 98%, and each additional 9 of closure costs disproportionately more hardware, more power, and more complexity, all of it imported. And even if it worked perfectly, the result would be a sealed population of fixed size, unable to expand, unable to replace anything it lost. That is survival, and it is not settlement. Two items on the third list deserve to be looked at directly, because they are the clearest examples of a capability that cannot be localized at any settlement size anyone has proposed. Semiconductor manufacture is the first. A single modern chip requires ultra-pure water in large volumes, a dozen high-purity gases, photolithography equipment built to tolerances measured in fractions of a wavelength of light, clean rooms with particle counts far below anything a dusty world could hope for, and a supply chain that draws on most of the periodic table. It is arguably the most complex thing our species does, and it is done in a handful of places on Earth by an industry employing hundreds of thousands of people. A lunar settlement will not be making chips. It will be receiving them, in boxes, from a planet, for as long as it has computers. Pharmaceutical synthesis is the second, and it has an additional cruelty. Complex organic molecules require carbon feedstocks the moon does not have, and reagents it cannot refine, so drugs must be imported. And imported drugs degrade under radiation exposure during transit and storage faster than they would in a terrestrial warehouse. So stockpiling, the obvious answer to a long supply line, is only a partial answer, because the stockpile is quietly expiring the whole time it sits there. It also helps to see that independence is not a threshold that gets crossed once and then held. It is a set of ratios. What fraction of water is recovered? What fraction of air is retained? What fraction of parts can be repaired locally? What fraction of calories comes from the farm? Every one of those ratios has a value today, and every one of them gets worse as the settlement grows, unless a new local source is found for the thing being consumed. A settlement does not become independent by getting larger. It becomes more dependent, more efficiently. And there is a pattern in the literature that is worth stating plainly. Every architecture that closes the ledger on paper does so by assuming a volatile supply from somewhere other than the moon. Every single one. That assumption is usually stated briefly, in a sentence or two, near the end of a very long document, and it carries the entire result. The problem is never solved on the moon. It is relocated. Underneath all three roots sits a subtler dependency that no amount of chemistry addresses. The most irreplaceable import is not a material at all. It is skill. A modern technological society assumes a depth and breadth of human expertise that is held collectively by millions of people, and a settlement of a few hundred cannot contain it. Automation shifts the problem sideways rather than solving it, because every robot that replaces a specialist adds a population of components that a different specialist has to maintain. The settlement's minimum size is set from below by the skills it must hold, and from above by the resources it must import. There is no guarantee that those two bounds leave any gap between them at all. It is worth noticing what is not on the list of obstacles. Energy is not the limiting factor. Nuclear power can supply everything described here, and the moon has no shortage of places to put a reactor. Building material is not the limiting factor either. The constraints that actually bind are element availability, thermal rejection, component manufacture, and human expertise, and none of the four is solved by trying harder or by spending more. There is a much weaker condition that a settlement could genuinely achieve, and it deserves to be named clearly, because it is often mistaken for the strong one. A settlement can be economically self-supporting without being materially self-sufficient. It can sell propellant to vehicles passing through, sell research access, sell shielding mass and manufactured bulk goods into orbit, and earn enough to pay for everything it imports. That is a real and achievable business, and it is the likely shape of any lunar presence that lasts. It is also, precisely, a place that pays its import bill, rather than a place that does not have one. Every terrestrial community that has ever achieved true self-sufficiency did so at a technological level far below the one a vacuum habitat requires. A village can feed and clothe and house itself with local materials because a village does not need semiconductors, pressure seals, cryogenic pumps, or a manufactured atmosphere. The moment a community needs those things, it needs the industrial world that makes them, and the industrial world is a planet. That is the whole ledger. Local abundance in everything that is cheap on Earth, and local absence in everything that is indispensable everywhere. Part 13. The Trap, named gently. So we come back to the word in the title, and it is worth handling carefully, because the moon does not deserve the drama the word implies. A trap, in the ordinary sense, involves intent. Something is baited. Something closes. There is a moment when the situation changes from open to shut. Nothing of that kind happens here. The moon has no mechanism, no timing, no interest in the outcome. It has been exactly what it is for 4.5 billion years, and it will go on being exactly that long after every question in this audit has stopped mattering to anyone. What it has instead is a shape, and the shape is the thing worth remembering. The moon is close enough to reach, which is why we keep going. It is rich enough to start on, which is why the plans always look plausible. Its ground is nearly half oxygen. Its poles hold water and near constant sunlight side by side. Its soil will pile into shielding, sinter into paving, and melt into metal. Every one of those is real, and each of them makes the first step easy in a way no other world can match. And then, quietly, it turns out that starting is all it ever permits. The air needs a gas that is not there. The water is a balance, not a cycle. The good ground amounts to a few ridges. The soil that shields the habitat also grinds it down. The machines age with no factory behind them. The bodies adapt in a direction that cannot be undone. The children cannot be authorized. The food is manufactured from imports. The heat sets a ceiling nobody expected, and the planet that supplies all of it hangs motionless in the sky, 3 days away and permanently out of reach. That is not hostility. It is insufficiency, and insufficiency is patient. It does not have to do anything at all. The settlement does the rest, growing, committing, spending, and discovering that every year of success has deepened its need for the world it can see and cannot get back to. There is a gentler way to hold all of this, and it is not a consolation prize. It may be the actual answer. The moon may be exactly as valuable as a doorstep is. Not a place we will move to. The place where we find out what moving would require. Consider what that is worth. Every constraint in this audit is a lesson, and each one is delivered at the shortest possible distance from home. A closed loop that fails on the moon fails while help is 3 days away rather than 3 years. A shielding assumption that turns out to be wrong is discovered by people who can be brought back. The first attempt at growing a full diet under lamps, the first decade of machinery aging in vacuum, the first honest measurement of what 1/6 gravity does to a human skeleton over years, all of it can be learned there, expensively but survivably, before anyone stakes a crossing to somewhere that offers no return at all. There is a useful comparison closer to hand, and it is quietly instructive. Every permanent human presence in an extreme environment on our own planet works the same way. The polar research stations are resupplied by ship and by aircraft, their people rotated on a schedule, their fuel and food and spare parts flown in across a continent. The deep ocean platforms, the high-altitude observatories, the remote islands with a few dozen residents and a supply vessel 4 times a year. Not one of them has ever become independent, and not one of them was ever expected to. They are outposts, staffed by people who go home, in environments that are gentler than the moon by an enormous margin. Every one of them has air outside the door. It is worth remembering, too, how little time we have actually spent there. The moon has been in the sky for 4.5 billion years, and the total duration of every human visit to its surface, added together, comes to a handful of days. 12 people have stood on it. Nobody has ever spent a fortnight. Everything in this audit is an estimate built on that, on a few days of direct experience and a great deal of careful inference, which is a reason to hold all of it lightly. Seen that way, the trap is a teacher. Everything the moon refuses to supply is a question our species has never had to answer, and it is asking those questions in the only place close enough that getting them wrong is not fatal to everyone involved. And there is something quietly worth admiring in the moon itself, underneath the ledger. It has been keeping one face turned toward us since long before there was anyone here to notice. It has taken the impacts that would otherwise have found us, held its shadowed craters at a temperature colder than Pluto for 2 billion years, and preserved in them a record of where the water in our oceans came from. Its surface keeps every mark ever made on it. The footprints from our brief visits are still there, sharp-edged, undisturbed, with no wind and no rain to take them away, and they will still be there in 10 million years. Whatever else the moon is poor in, it is extraordinarily rich in memory. The same absence that makes it so difficult to live on makes it the finest archive our species has ever had access to. No weather, no erosion, no burial. A world where nothing is taken away. Whatever we eventually build there, or fail to build, will still be standing in some recognizable form when the continents down here have rearranged themselves and every city we have ever made has been ground back into sediment. The moon does not preserve things carefully. It simply never disturbs them. Perhaps that is the fairest way to end the audit. The moon is not a second home and was never going to be one. It is the nearest hard thing, a place that will let us practice and will not let us settle, holding the beginning of everything and the end of nothing, entirely without malice, for as long as we care to keep arriving. And in the sky above whatever we build there, Earth will go on hanging in the same patch of black. Not rising, not setting. Blue and white and turning slowly, with weather crossing it, in full view of everyone who has ever stood on that grey ground, and no closer for being seen. Let that be where we leave it tonight. Nothing about the moon is in a hurry. It has waited 4.5 billion years for us to work any of this out, and it will wait a good deal longer without minding at all. There is no urgency in any of it, and nothing to decide before morning. So the moon keeps doing what it has always done, which is very little, patiently, for as long as anyone cares to watch. It offers the beginning of everything and the end of nothing, and it will go on offering exactly that, whether or not we ever accept. Let the day settle out of your shoulders. Let your breathing slow, and let the light behind your eyes grow dim. Sleep well, and good night.